So now we're going to begin our discussion of lipids. The word lipid comes from lipos, meaning fat. Biological lipids are either hydrophobic, purely hydrophobic, or amphipathic. What does amphipathic mean? That means that they have both a polar and nonpolar region. So they are both hydrophobic and hydrophilic. These are the classes of lipids: fatty acids, triacylglycerol, glycerophospholipids, sphingolipids, waxes, and isoprene-based lipids. We will look at all of these except waxes, because waxes really aren't are molecules that concern us with our metabolism discussion. So we're going to look at the saturated fatty acids. So you're going to need to know the common names and the structures for fatty acids up to 20 carbons long in the saturated class. What does saturated mean? It means that all the carbon-carbon bonds are single bonds, and the carbons are fully saturated with hydrogen. So there's free rotation around those single bonds, thus these molecules are going to be flexible. The list of saturated fatty acids that you need to know is here: lauric acid, myristic acid, palmitic, stearic, and arachidic acid. So 12 up to 20 carbons. We're going to look at some notation for these, but palmitic and stearic acid are the most common saturated fatty acids. So they have 16 or 18 carbons. So what is a fatty acid? Basically, in general, it's a carboxylic acid with a long chain hydrocarbon side group. At physiological pH, they are ionized to that carboxylate group, so C double bond O, O minus. And we'll take a look at different ways to represent these. Typically, I'm going to ask you to draw these as line angle formulas, and we'll be drawing lipids together at the end of this discussion. The unsaturated fatty acids contain one or more double bonds in that hydrocarbon chain. They're actually slightly more abundant in nature than the saturated fatty acids. But what does the introduction of that double bond do? These, well, obviously there aren't rotations around a double bond, and they are a bit more rigid than and less flexible than those saturated fatty acids. So these are, let's see, I want to make sure you're going to be responsible for all of these except the gamma-linoleic acid, number 18,3. And again, this is the notation that actually, I forgot to mention notation here. Let's take a step back. This is the notation that is used to describe saturated fatty acids. So this 12 tells me I have 12 carbons, and we have the colon, and then we have a 0. That 0 means there are no double bonds. So all of the saturated fatty acids are going to have 0 in their notation. The unsaturated fatty acids have a double bond. So there are 16 carbons in palmitoleic acid. There is a double bond, one double bond. So this reflects the number of double bonds. So here we have 1, here we have 2, here we have 3 and 4. And then this part of the notation tells me where that double bond is in that structure. If you look at the numbers or the locations of those double bonds, you should notice a pattern here. When there are double bonds, they occur about every 3 carbons. And I'm sure you've probably heard the term, omega-3, omega-6 fatty acids. We'll look at those too. And what this means is the last double bond for 3 or 6 is 3 or 6 carbons from the number 1 methyl group at the end of the chain. And I'll point this out as we're looking at and drawing these structures together. So you can ignore this notation. We're going to use the notation that I've shown you previously. Obviously, this is the same as what we did what I showed you before for the saturated. The point of this slide is I want you to take a look at the melting points. Okay. So melting point gives us an idea of how many intermolecular forces are at work here in these molecules. So if you remember London forces or van der Waals forces, they're the weakest of the intermolecular forces. And these molecules would have London forces or van der Waals forces. And remember, as chain length grows or the size of the molecule grows, those forces grow too or increase. So what the trend you see here is as carbon numbers increase, so do melting points. So if we have a carbon chain with 12 carbons, melting point is 44.2 Celsius versus 24 carbons, it goes up to 88. And if you compare the saturated melting points for saturated fatty acids to the unsaturated fatty acids, you see that these are much lower. So when you introduce that double bond, these molecules are not going to be able to pack as tightly together. So here are two of our saturated fatty acids. Line angle formula is given here, and this is the way I want you to draw these structures. This is about a space-filling model, but you see that these are linear, very straight, even though we've got these little crooks here in the line angle formula. These are solids at room temperature, and that is due to their ability to pack tightly together. So these types of fatty acids would be found in lard or butter. So increased melting point because we have increased IMFs or intermolecular forces over that long chain. Here are two saturated fatty acids, and you can see that where that double bond has been introduced, we have crooks here, or bends in our structures. This one has two, so we've got this real hook at the end. This is an omega fatty acid, but again, we'll look at when we draw these structures together, we will talk more about that. The other thing I want you to note here is these are cis double bonds. So in all but one of the fatty acids we look at, we are going to have cis double bonds. So all the saturated fat or unsaturated fatty acids we're looking at right now are going to have cis double bonds. These are liquids at room temperature, so they're oils. So this is just a table that gives you some idea about the compositions of some of the dietary lipids that we consume. Remember, these two are unsaturated. These are saturated. So would you, well, let me see. These 57 to about 43 is the ratio of saturated to unsaturated. So we've got greater saturated to unsaturated in beef and milk here. So these are more solid, for example. sources of protein or of lipids. In this section, we have oils. So these are very heavy percent unsaturated fatty acids. So as I said, we're going to take a look at some trans fatty acids. The top picture here, allylic acid, it has a trans double bond at 9. So the 9 actually represents the first carbon in that double bond. So if we count from the carboxylate end, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So when we look at those notations, the number representing the double bond is going to be the first number in that, or the first carbon, number carbon in that position. So this fatty acid is not very good for us, and it is a result of hydrogenation. So the process of hydrogenation adds hydrogen atoms to the cis double bonds in fatty acids. However, during the process, it also converts cis double bonds to trans double bonds. So processed fats like margarine are made by partial hydrogenation of polyunsaturated oils that contain substantial levels of trans fat, unfortunately. So this is the principal trans fat found in hydrogenated vegetable oil products. The other, becenic acid, is a naturally occurring trans fatty acid, and this occurs in the fat of ruminant animals, which we've already discussed, and in dairy products. So this would be in milk, butter, cheese, and meat. So we're very aware these days of good fat, good cholesterol, bad cholesterol. So as the trans fatty acids have increased in our diets, it increases the plasma level of LDL, which is the bad cholesterol, and decreased the levels of HDL, or the good cholesterol. So what is the storage molecule for these fatty acids? Triacylglycerols. So we can also call them triglycerides, and it is the major energy storage in mammals, and these are stored in adipose tissue, which again is lipid storage. These are composed of the glycerol molecule, and you'll see glycerol has 3 hydroxyl groups. And when we form that triglyceride, we're going to attach a fatty acid through that hydroxyl group. So this is an esterification reaction. These fatty acids could all be the same, or they could be 3 different ones. They could be any combination of fatty acids that we want if we're making them ourselves. If they're all the same, they're called homotriglycerols. If they are not all the same, they would be hetero. And again, this is a condensation or esterification reaction, and we'll take a look at that. These can also be hydrolyzed, because what's the point of storing these molecules if we can't use them? So that means we have to be able to free those, free those fatty acids when we need energy from lipids. So this is done in a stepwise manner. If we hydrolyze 1, we're going to have a diacylglycerol. If we hydrolyze 2, we will have a monoacylglycerol. So I like to, if possible, relate this to something that is natural, or something about concerns that we have about, for example, in lipid intake or carbohydrate intake. But polar bears, ironically, fast 8 or more months during the year. So that means that they consume no food and no water. All the water around them is too cold or too salty, the ice too, and they produce all the water they need from the metabolism of fat. Historically, their normal diet is only fat from seals that they catch. Now, unfortunately, they might be finding other sources of food these days, but they rely entirely on the metabolism of fat to produce all the water and the ATP that they need. So they don't urinate, they don't defecate, and they go muzz without doing so. They recycle their own proteins to make new proteins as well. Polar bears burn up to 1.5 kilograms of fat per day, which is 3.3 pounds of fat per day. That is something I wish I could do. Okay, so glycerophospholipids are basically derivatives of lipids, specifically of phosphatidic acid. This is the largest and most important class of natural lipids that we will look at. So this is the parent phospholipid, so phosphatidic acid. Here's that phosphate group, and you see it just has 2 side chains here. We can change the head group. So essentially, add a head group, I should say, not change it. So parent molecule to this phosphate group, if we add this particular head, ethanolamine, we have phosphatidyl ethanolamine. Phosphatidylserine, so this is a serine head group, and phosphatidylglycerol. So we've added a glycerol molecule here. So if I wanted to describe this generally, I would call this a 1,2-diacylglycerol. So this is carbon 1 and 2. With the phosphate group in carbon 1, 2, 3. Phosphate group is in the 3 position. Sorry about that. So these 3 phosphatidic acids that we're looking at are essential components of cell membranes. And phosphatidic acid then is the parent compound of all those glycerol-based phospholipids. We will look at, these are the 2 most common cell membrane phospholipids, and phosphatidylserine is also in there too. Phosphatidylcholine, we haven't gone there yet. PE, okay, we're going to call this PE, PS, and PC. Phosphatidylcholine and phosphatidylethynolamine are the 2 most common phospholipids in cell membranes. This is also in the membrane, but we'll discuss where it is located when we talk about membranes. So I want you to be familiar with phosphatidylcholine, phosphatidylethynolamine, and serine. Just in general, knowing it's the derivative of phosphatidic acid, its content in membranes, which again we will talk about, but here are 2 other glycerophospholipids. This is cardiolipin. This is found in heart tissue, and phosphatidylinositol. I don't think we'll see that anywhere actually. Sphingolipids. They are another form of a lipid derivative. And these are based on the structure of sphingosine, which we see here. And we will also be drawing, drawing this together. Sphingolipids are also membrane components, and there are some derivatives, other derivatives of sphingosine. Let's see. Sphingosine itself. We see we have some hydroxyl groups here, we have an amino group here, and then we have an acyl side chain. So this is just the backbone of sphingosine. Some of the other derivatives we're going to look at are ceramides. We're going to have a fatty acid linkage through that amino group here. And again, you'll have to be able to draw sphingosine, but I will not have you draw any of the derivatives, but understand where the linkages are and perhaps where they're used. So what are some glycosphingolipids? These are going to be ceramides, so we'll have a fatty acid here, but we're also going to have a sugar attached through one of these hydroxyl groups. A cerebroside is a single glucose or a galactose that is going to be linked through this hydroxyl group. Gangliosides are the most common glycosphingolipids, and that has the ceramide backbone, but also 3 or more sugars attached to it. You'll find in nerve tissue sphingomyelins. These are phosphate esterified and have polar heads. And I'm not sure we'll take a close look at those, so don't worry about those at the moment. Anything else I wanted to say here? No. All right, moving on then. The ceramide, which we're now looking at here, we've got some kind of lipid attached to that amino group, and again, this R chain is going to represent an alkyl group, are then going to be the parents of the sphingomyelins and their cerebrosides. So another very, very important molecule that is lipid-based or isoprene-based are steroids. We'll look at steroid hormones. This core structure of 3 6-membered rings and 1 5-membered ring all fused together are the basis for building steroid hormones and cholesterol. Cholesterol is the most common steroid in animals and a precursor for all of the other steroid hormones or steroids in animals. So while you may be familiar with some of the functions of steroid hormones, you're probably not aware of the fact that they help with the salt balance, metabolic functions, and obviously the one you're familiar with, at least most are, sexual function. So this is the structure of cholesterol. So this is the sterol part of that molecule. I'm not going to go into the reactions that produce cholesterol, but there are 27 steps in the process that builds that cholesterol molecule. And these are some steroids that are also important. There are basically 5 steroid hormone families. We're only looking at 4 here. Androgen, progestins, so androgen is not here, glucocorticoids, mineralocorticoids, and bile acids. Androgens consist of testosterone and estradiol, two sex hormones that you should probably be familiar with. Progesterone or progestin regulates and plays a role in estrus and pregnancy, and cortisol's control carbohydrate, protein, and lipid metabolism. So cortisol is a glucocorticoid. Sorry. I mentioned mineral corticoids. These are involved in salt regulation in tissue, and bile acids are detergent molecules that are secreted in the bile from the gallbladder, and these assist in lipid absorption. Progesterone is a precursor to both testosterone and estradiol. Not sure if you knew that, but take a look at estradiol versus testosterone. We've got a hydroxyl group here that's replicated here. The only difference is in this part of the ring where we have a carbonyl group. Here we have a hydroxyl, which affects the double bonding in this ring. So this can be reduced, testosterone can be reduced to estradiol, and that is a process that occurs naturally. And that concludes our discussion of lipids.